In this video, we're going to continue to look at the Diels-Alder reaction and use molecular orbital theory to understand the mechanism. So one way that we can try to study reactions, and in particular the Diels-Alder reaction, is to apply frontier molecular orbital theory. So with frontier molecular orbital theory, we are focused on the highest occupied molecular orbitals and the lowest unoccupied molecular orbitals, right? We don't otherwise care about orbitals that are otherwise occupied or otherwise unoccupied, just the ones at the frontiers. Because we always think about reactions being driven by electrons, then the flow of electrons has to go from the occupied molecular orbital of one reagent into the unoccupied molecular orbital of the other reagent. Let's look at the molecular orbitals of our two reagents, ethylene, our dienophile, and 1,3-butadiene, our diene. You can look back at slides 5 and 6. When we think about ethylene, we have two p orbitals, so they can be both up in phase, or they can be one up, one down. This one is pi 1, this is pi star 2. We have two pi electrons, so we fill those in. They are both in the pi 1 molecular orbital. Therefore, this one is the highest occupied molecular orbital, and this one is the lowest unoccupied molecular orbital. Now, if we look at butadiene, we have four p orbitals, so they can be all up. You could have two up and then two down, one up, two down, one up, one up, one down, one up, one down. This one is our pi 1, pi 2, pi star 3, and pi star 4. We have four pi electrons, so we fill those in starting at the bottom, and this is what we have. So that means this one, the pi 2, is the highest occupied molecular orbital, and then we have the lowest unoccupied molecular orbital as well. So if we are thinking about frontier molecular orbital theory, we need to have electrons going from an occupied to an unoccupied. We still don't know whether the reaction flows from the highest occupied molecular orbital of the dienophile to the lowest unoccupied of the diene, or does it go from the highest occupied of the diene to the lowest unoccupied of the dienophile. Now, for both of these little schematics, we are looking at energy increasing in this direction, and we are looking at energy increasing in this direction, but this is not necessarily on the same scale as this. So I'm not trying to show the relative energy levels of this LUMO compared to this HOMO, or this LUMO compared to this HOMO. In order to figure out which way the reaction goes, whether it is HOMO to LUMO or HOMO to LUMO, we need to look at some other information. So we'll come back to this in a minute. Let's talk about some experimental evidence related to a series of Diels-Alder reactions. So if we call our first one our standard, so let's say we're carrying it out at 200 degrees at a particular amount of pressure, and we want to figure out how long does it take the reaction to go to completion, for example. Well, if we carry out these other reactions under the same conditions, do they happen faster or slower than our standard reaction? So this first one, we are looking at having an aldehyde on the diene. This one reacts slower than the standard. And the second example, we have an aldehyde on the dienophile. This one happens faster than the standard. On the right side, we have, again, a diene. In this case, we have methyl groups on the diene, and this one happens faster than the standard. And in our last example, we have methyl groups on the dienophile. This one happens slower than the standard. Let's think about an aldehyde. Is that an electron releasing group or an electron withdrawing group? Well, the oxygen is more electronegative than the carbon, so it will be pulling electron density towards it, which means this carbon is going to be trying to pull away electron density from its neighbors. So an aldehyde is an electron withdrawing group. Notice when it is on the diene, so the first example, it decreases the rate of the reaction, but when it's on the dienophile in the second example, it increases the rate of the reaction. Now, let's take a look at the methyl substituted compounds. The methyl group is an electron releasing group. An sp2 hybridized carbon is slightly more electronegative than an sp3 hybridized carbon, so this will be pulling electron density towards it. So methyl group is an electron releasing group. Notice when it's on the diene, it increases the rate of the reaction, but when it's on the dienophile, it decreases the rate of the reaction. So if we look at this information together, we can see that the reaction works better when the diene is electron rich. When there's an electron withdrawing group on the diene, it slows it down, but when there is an electron releasing group on the diene, it speeds up the reaction. And the reaction works better, it works faster, when the dienophile is electron poor. Sorry, I lost my arrows here. So what does this tell us then? What is the direction of flow of the electrons? Well, they must be flowing from the electron-rich diene to the electron-poor dienophile. So they're flowing from the diene to the dienophile. How does this happen? Well, now let's go back to the frontier molecular orbital theory. Now from the previous slide, talking about the relative reactivity, we saw that the flow of electrons must go from the diene to the dienophile. And earlier, when we were talking about frontier molecular orbital theory, we said that the flow of electrons must proceed from the highest occupied molecular orbital of one species to the lowest unoccupied molecular orbital of the other species. In other words, what we see is that we must be talking about the highest occupied molecular orbital of the diene reacting with the lowest unoccupied molecular orbital of the dienophile. On the left, we have our dienophile, and we need the lowest unoccupied molecular orbital. So here we have one up and one down. And for the diene on the right, we need the highest occupied molecular orbital, and that's the one that has two up and two down. So for this reaction to work, let's think about our diene. Here are the orbitals, and so we've got two down and two up. And we need to have the dienophile approach, and here we can have one down, one up. That's the same as having one up, one down. But notice what this gives us. So our p orbitals can align so that these are in phase and so that these are in phase, right? If you had one of them dark, one of them light, then that would be out of phase. But this way, the p orbitals can come together end to end in phase, and that allows for the sigma bond to form. Right, so we have in-phase orbital overlap, allowing the reaction to occur. Ignore this picture from the book. So the big picture here is that We are using molecular orbital theory, in particular frontier molecular orbital theory, to figure out which molecular orbitals react with which molecular orbitals, and then because we have in-phase orbital overlap, the reaction works. So let's take this information that we learned about the Diels-Alder reaction and put it into practice as we are trying to prepare a particular target compound. So let's say we want to make this compound with a 6-membered ring substituted with 2 ethyl groups. Well, we know that we can reduce an alkene, so that means that this compound could be prepared from this compound or from this compound or from this compound, etc. And we know that any of these could be obtained via the Diels-Alder reaction. So which way would we want to set this up? Well, the ethyl group, like a methyl group, is an electron releasing group, so we want to have an electron releasing group on the diene. So we would try to carry this out where here is our diene with the ethyl group and the ethyl group, and that would react with ethylene. We'd carry out the Diels-Alder to give us this product, and we do it this way because we expect that it will be a successful reaction. And then once we have our Diels-Alder adduct, then we can just treat this with hydrogen and palladium to give us the target. All right, so use what we know about the Diels-Alder. Don't forget that the Diels-Alder gives a product with an alkene, so it would require one more step to make a cyclohexane. In the bottom example, we have a nitro substituted cyclohexane. Because we have a 6-membered ring, we know that we could make this from a 6-membered ring that also contains an alkene. And we know that we can make this 6-membered ring by a Diels-Alder reaction. So we might want to make it from this compound or this compound, where maybe that's where the alkene is, or this one where the alkene's over here, etc. Let's think about this. The nitro group, this is a very strongly electron withdrawing group. Oxygen is stealing electron density from the nitrogen is stealing electron density away from the carbon, so the nitro group is an electron withdrawing group. So we want the electron withdrawing group to be on the dienophile, not on the diene. So we could set this up where we are using butadiene reacting with nitroethylene, and this can undergo the Diels-Alder reaction to give us this product. And then if we treat this with hydrogen and palladium, we'd have to be careful with the conditions to make sure we reduce the double bond and not the nitro group. But that can give us this, which is our target. So if you can use the Diels-Alder reaction to make a particular target compound, make sure that, if possible, you think about whether you would want particular substituents on the diene or the dienophile in order to make the reaction most likely to succeed. So this takes care of our chapter on dienes. We learned a little bit about their characteristics, how to make them, and how they react, including some reactions that were analogous to what we saw for alkenes. But we've got the Diels-Alder reaction, which it's a really cool reaction that happens with conjugated dienes.